Hello, welcome to this course on TinyML with Arduino. In this session, we will explore hello world examples. It's the first step for our running machine learning in the microcontrollers. And I am Ramanan. I am here to guide you through this theory, code and course hands-on development. Let's get started. Just as traditional programming, where hello world is a very first program we'll write to test our setup, we'll also use hello world here to test the entire machine learning pipeline from data to the deployment. Our goal is here very simple. Train a model on a sine wave and run it on an embedded device, specifically Arduino Nano 33 BLE Sense. Through this, you will see how an AI model can fit inside microcontrollers. Small chip with very limited resources and still can perform meaningful computations. Here, what makes this exercise very powerful? We are not just running a machine learning model in a Python. We are just actually deploying it in a hardware. We'll use not just Python, we'll use TensorFlow, Google Colab to build a complete model, and we'll run it on Arduino Nano 33 BLE Sense. This process teaches you how to bridge two worlds, software side of AI and also hardware side of embedded system. Whether you are hardware engineer or software engineer doesn't matter. You will see two perspectives come together as a single. So ask yourself, how amazing is that? The same TensorFlow library that runs on huge servers can also run a tiny microcontroller with just few kilobits of memory. It also run a trained model on a Arduino Nano 33 BLE Sense and see how machine learning runs on a low power devices. This slide outlines a full TinyML workflow. So here we are going to guide through the full journey of TinyML projects. You will build a simple neural network that predicts a sine wave, convert it into embedded format and run it on a real hardware. It's a simple, approachable, complete ML experience. So first we are going to create a data set. In this case, sine wave using NumPy in Python. Next, we are going to train a neural network with Keras. Keras is like an Arduino IDE for AI. It hides the complexity and let us focus on the structure. Then we evaluate the model performance. We'll use metrics like MAE to measure accuracy. The trained model is converted to TensorFlow Lite format, which compresses so that it can fit into microcontroller memory, so that the file turned into C array using a tool called XSG. This allows us to embed the model directly into the Arduino code. We'll compile this firmware and upload it to Arduino. Finally, we run it live, watching the predictions unfold in the real time. Before driving into your training, let's pause and ask, why do we choose sine wave in the first place? So, the question is, why a sine wave? Normally, if I wanted the value of x, I could just use some math library. So why train a model for it, use a AI for it, and to predict a sine wave? The reason is practice. A sine wave is a continuous, smooth and predictable, making it ideal for regression tasks, where we can predict continuous values. And it's also easy to understand and visualize. It's a clean way to introduce this AI in training, testing and inference. It also gives instant feedback visuals. You can plot the predicted versus actual values and immediately see how well the model is performing. This example sets a foundation. Later, instead of sine waves, we'll use some sensor data like accelerometer or microcontroller input. So think it as a training wheels for TinyML. Once you can predict a sine, you are ready to predict a real world signals. So here in this code, we are going to use a single float x and also output predicted as sine x. So this model learns from this smooth and continuous pattern, gives immediate visual feedback, ideal for exploring regression tasks. So here is the predicted x sine wave. To make this workflow possible, we are using a combination of software tools, most of which are open source. So first is Python and NumPy, helps us generate and manipulate the data. Next is matplotlib, let us plot and visualize the data. And next is Keras. So we build the model with the TensorFlow and Keras, especially Keras, it's actually user friendly for neural network creation. So for all the coding happens in the Google Colab. This avoids the pain of installation, just open notebook and you can run it easily. When the model is ready, we'll use the TensorFlow Lite, convert and shrink it. Then XSD converts the file to .tft lite. to a C array. And finally, the Arduino IDE compiles and uploads everything to Arduino Nano 33 BLE Sense. Now that we know the tools, let's see how entire ML hardware pipeline connects. So overview of ML to hardware pipeline. This slide shows the big picture end-to-end pipeline. Step 1. Generate data. Here we simulate the sine wave value using a NumPy. Step 2. Train the model with Keras, teaching it perfect sine. Step 3. Validate performance. Check if the prediction matches the true value. Step 4. Convert it to TF Lite. This makes the model small enough for microcontroller. TF means TensorFlow Lite. Step 5. Convert the C array using XSD, embedding the model into Arduino code. So this is the exact same flow used for real embedded ML. Only the dataset and model complexity changes. For now, we'll master the sine wave so that we can handle more complex text later. So far, we have seen the big picture what we are building, from generating a simple sine wave dataset, training a model in Python, converting it to lightweight format, and finally preparing it for deployment. So you understand why we use a sine wave. It's a simple way to practice regression, visualize the prediction, and build confidence to move into real sensor data. We also looked at the tools like Python, TensorFlow, Google Colab, Arduino IDE. So these tools are the foundation for every TinyML workflow. In the next video, we'll dive deeper into the training process itself. We'll talk about the model structure, training metrics like loss and MAE, how to interrupt the performance of the model. We'll set the stage for deploying and running a first TinyML applications. Thank you.